From Johannes Kepler's elliptical orbits in the 1600s to contemporary physics and robot control systems, researchers have long sought closed-form expressions that explain observations, but uncovering the equations that govern data remains a formidable challenge. Symbolic regression promises interpretable models, but existing methods often struggle with convergent speed and structural reuse. In this video, we demonstrate SymMatika, a new model for symbolic regression leveraging structure-aware symbolic discovery, or both explicit relations and implicit physical laws in data. Let's walk through how SymMatika works. We begin with some input data, and we determine the system type. Specifically, we determine if we search for explicit mappings or implicit relations. Most existing symbolic regression models specialize in either one, but not both. The only known system supporting both, Eureqa, has remained closed-sourced and now is integrated into a commercialized platform. Our code is 100% open-sourced on our project website. Now, if explicit, the data will contain input variables and a corresponding target variable, and we search for an explicit mapping of inputs to the target. For example, look at this character throw a ball. We can measure inputs such as the angle and velocity the ball is thrown at, and we can also measure the height of the ball over time, which is our target variable. We can explicitly map these inputs to a known target variable. For implicit relations, there is no known corresponding target, and so we search for invariants in the system modeled by the data. For example, consider the pendulum to the right. We can measure the angle from the center axis and the velocity of the pendulum, and use this information to find a physical invariant, such as a conservation of energy law. We then use a parameterized candidate generator theta to build a set of initial populations. Each island has its own set of candidate parameters, which are updated during the evolutionary search. Islands are then individually evolved with iterations of genetic programming, and at fixed intervals of iterations, we diversify the island populations through small, controlled migrations between populations. This allows distinct and independently evolving islands to share valuable information through the migrated individuals. These islands are then fed into the central reusable structure library, which we henceforth call the Motif library, given its inspiration from biological sequence motifs. We select the top-performing individuals in each island and perform a structural analysis to search for high-impact substructures. SymMatika uniquely identifies structure-level trends that meaningfully impact loss, as opposed to only parameter-level trends that previous symbolic regression models have employed. This allows for the discovery of larger and more impactful positive trends in the evolutionary process. Consider the following example. Suppose we have two top-performing candidates. We perform the motif search and discover that the terms 3x squared and 2y have large impacts on their respective candidates' low loss. We then isolate these motifs and add them to the motif library. We then recombine these terms and produce composite expressions from these motifs. Essentially, we are building full solutions from partial solutions. The fittest composite expressions are randomly injected back into the island populations, and a small population of top performers is updated with the fittest individuals across all islands. This evolutionary cycle continues until either an individual reaches sufficient near zero loss or the set number of cycles completes. SymMatika demonstrates impressive capabilities to discover explicit mappings in data, as exhibited by our performances on the Nguyen problems and the Feynman equations. On the Nguyen benchmark, it achieves a 96.5% average recovery rate, including a 61% success rate on the previously unsolved Nguyen 12. On the Feynman equations, it solves 72 of 100 problems, matching state-of-the-art performances from various neural and language-guided methods. SymMatika also demonstrates its ability to discover physical invariants in the Eureqa physical systems, converging up to 100 times faster than the original Eureqa model, all without GPUs or LLMs. For easy use and applications, we've developed a user-friendly GUI for scientists and curious people alike to easily explore and discover fundamental governing laws in data and to develop interpretable models through structure-aware evolutionary search. For more information, please refer to our paper and project website.